ABC is a triangle with BC is equal to 5. D is the foot of the perpendicular from A on BC. E is a point on CD such that B is equal to 3. The value of AB square minus AE square plus 6CD is. Now, purely looking at this question, you might find it a little difficult the moment you see this part. But let's try plotting everything that they have given. So we know ABC is a triangle. Let's say this is A, B, C. Such that BC is equal to 5. So this entire part is 5. Right. D is a foot on the perpendicular from A on BC. So we have here D, perpendicular, and E is a point on CD such that BE is equal to 3. So there is a point BE, could be anywhere, let's say here it is, this is E, BE is equal to 3. The value of AB square, we have to know AB minus AE square. So let me draw a line here, AE square plus 6CD. Okay. Now, if you notice, we have two right angle triangles, in fact 3 right angle triangles. We have triangle ABD, we have ADE and ADC. I know I can bring AB square from there and also have AE square. So let's write AB square is the hypotenuse of ADB. So that gives you AD square plus BD square. And similarly, we have AE square is equal to again AD square plus DE square. Now we need AB square minus AE square. So we can simply subtract this equation. So you will get AB square minus AE square is equal to AD square gets cancelled. We'll be left out with BD square minus DE square. We need to know the values of BD and DE. We know BE is 3. This entire part is 3. So let's say BD is X. So DE becomes 3 minus X. So BD is equal to X. DE is equal to 3 minus X. We can take that. Now we substitute this value over here. We get X square minus 3 minus X the whole square. So you solve for it, you get X square minus 9 minus 6X plus X square. We'll have minus 9 plus 6X minus X square, multiplying the minus inside. So X square minus X square goes off. So we are left out with AB square minus AE square as 6X minus 9. So we have figured this out. The question also has 6 CD in it. If we look at CD, we need a value for CD. Now we know this entire BC is equal to 5. We also know BD, we have marked it as X. So CD automatically becomes 5 minus X. That's all. We have figured that one as well. Now we substitute this part over here. You get 6X minus 9 plus 6 into 5 minus X. CD is nothing but 5 minus X. So 6X minus 9 plus 30 minus 6X. Minus 6X plus 6X goes off. 30 minus 9 gives you 21. So option E. ABCD is a trapezoid where BC is parallel to AD and perpendicular to AB. Kindly know that BC less than AD. P is a point on AD such that CPD is an equilateral triangle. Q is a point on BC such that AQ is parallel to PC. The area of the triangle CPD is 4 root 3. Find the area of the triangle ABQ. So let's first plot the data that we have. The first thing that it says is we have a trapezium where BC is parallel to AD and BC is less than AD. And also AB is perpendicular to BC. We also have that. So we have a trapezium of this form, AD. This is 90 degree. So this is also 90 degree. Done. P is a point on AD such that CPD is an equilateral triangle. We have a point on AD called P such that CPD is an equilateral triangle. So all the three sides are equal. That we know. Q is a point on BC such that AQ is parallel to PC. So we have a point Q over here on BC. I connect AQ. This is parallel to PC. Now if QC is parallel to AP and AQ is parallel to PC, we clearly know that's a parallelogram. Two sets of parallel line intersecting. So it's a parallelogram. Automatically the opposite sides are equal. So CP and AQ, they both are equal in length. Now we know that. The area of this triangle is given. They are asking you the area of this triangle, which is easy. Now we know that CPD is an equilateral triangle. That means D is 60 degree. P is 60 degree. And C is also 60 degree. C in the equilateral triangle is 60 degree. Now ABCD is a quadrilateral. So that means the angle enclosed by the quadrilateral is 360 degree. We know this is 90, this is 90 and this is 60. 90, 90, 60 is 240. That means an overall angle of C is 120 degrees. But PCD is 60. That means QCP is also 60 degrees. Now since QCAP is a parallelogram, the angle enclosed over here is 120 degree. And automatically here is 120 and this is 60. And ABP is 90 degree. So BAP is 90 degree. That means BAQ is 30. This is 60. So we have a right angle triangle ABQ where B is 90 degree, A and Q, which is of the form 30 degree, 60 degree, 90 degree. A 30, 60, 90 right angle triangle will have the sides in the ratio 1 is to root 3 is to 2. If we can find out AQ, we can easily find the other two sides and we are through with that. Now I look at this triangle here, that's an equilateral triangle. So let's call PD as A. Now I'm going to find the area of this triangle. An equilateral triangle, when I draw the height, that automatically becomes the angle bisector of that angle and also the bisector of the opposite side. So this is A by 2. Now this is 60 degree, this is 90 degree, so this is again 30 degree. I have another 30, 60, 90. So that has to be, I take this triangle here, let's call this X. I take this triangle XDC. So here this is 30. That means this has to be 1 root 3, 2. I have this side as A by 2 because this is the half of PD. So this is A by 2. So this becomes 1 and this automatically becomes root 3 by 2A. Now from here we can figure out this area. Now I know area of CPD is equal to half of PD into CX. That is equal to 4 root 3. I know that this is half of PD is A into CX is root 3A by 2 is equal to 4 root 3. So root 3 gets cancelled. I have A square is equal to 4 over there becomes 16. So A is equal to 4. You know A is 4. If this is 4, I know that AQ also becomes 4. Now to find the area of ABQ becomes easy, where BAQ, this is 4. I know that 1 is to root 3 is to 2, where 2 is the hypotenuse. Instead of 2 I have 4. That means everything doubles. This is 2, this is 2 root 3. So this is 2 root 3 and this is 2. Now to find the area of this triangle becomes easy. Half of the base is 2 and the height is 2 root 3. So 2 and 2 gets cancelled. The answer is 2 root 3 square units. So the moment you know the basic angle side ratios 30, 60, 90 is 1 is to root 3 is to 2, this entire question becomes easy.
Ramesh and Reena are playing with triangle ABC. I really like that description, playing with triangle ABC. Nice. Ramesh draws a line that bisects angle BAC. Nice. Let's say ABC. Ramesh draws a line that bisects angle BAC and cuts BC at D. Reena then extends AD to a point P. Nice. Ramesh joins B and P. Oh, nice. This is a bisector. Ramesh joins B and P. Reena then announces that BD bisects angle PBA. PBA is bisected by BD, or this is equal to this. Together, Ramesh and Reena find that BD is 6, AC is 9, DC is 5, AC is 9, DC is 5, BP is 8, and DP is 5. How long is AP? We need to find AP. And nice question. It hinges on just one idea, angle bisector theorem. We know that AB by AC equals BD by DC. With that we can find AB. We know BA by BP is equal to DA by DP. Why? This is the angle bisector. In triangle ABP, BD is the angle bisector. The foot of the angle bisector cuts the opposite side in the ratio of the sides containing the angle. Plug the first one, find AB. Plug the second one, find AD. We know AD, we know DP, we can find AP. Nice. Let's jump in. 6 is to 5 is X is to 9. X is to 9 is 6 is to 5. X is 54 by 5. X is to 8 is AD is to 5. Or AD is 5 into X by 8. 5 into 54 by 5 by 8. 54 by 8, which is 27 by 4. Answers in decimal, so I'm going to get this in decimal. 6, 3 by 4, 6.75. 6.75 centimeters. Angle bisector theorem plugged twice over, nothing more than that. 6.75 plus 5, 6 plus 5 is 11, 11.75. Done. Draw a neat diagram, plug in angle bisector theorem once for ABC, plug in angle bisector theorem the second time around for BAP, and we are done, we are through. Two circles P and Q, each of radius 2 centimeters, pass through each other's centers. Lovely. They intersect at points A and B. A circle R is drawn with diameter AB. What is the area of overlap between the circles R and B? Excellent question. So, first circle, second circle. There's one center here, one center here. Right? This is say P and Q. They intersect at A and B. This is A, this is B. And then we draw a circle R with diameter AB. So we draw a circle like this. What is the area of overlap between the circles R and P? This circle is circle R. Let me see if I can put in a different color. We have the option. Why not do that? This is circle R. And so we want to find area overlapping between circles R and P. Okay. Let's see. Let's call this a circle R. We want to find area interlap between R and P. What will be the area overlapping between R and P? One will be this area. Okay. Nice. That is 1/2 of R. What will be the next one? That will be this area. That is some part of P. So, first of all, P and Q have radii 2 each. R radius we have to find, that depends on AB. After that, we know that this semicircle, that 1/2 of R sits inside P, and then this segment sits inside R. This segment of P sits inside R. This semicircle of R sits inside P. We need to find this area of overlap. And so, let's find AB first. We'll build from there. So if we have, let's go back to our black. This is 2, this is 2, this is 2. 2, 2, 2. 2, 2. Nice. So I know this triangle, it's an equilateral triangle, it's an equilateral triangle. This angle is 60, whole angle is 120. This is the altitude, let's say this, we call this point as two circles, the centers, they intersect at A and B. Let's call the centers as C and D. And this point is E. AE is equal to root 3. Why root 3? Root 3 by 2 times side is the altitude. This is an ACD is an equilateral triangle. 2, 2, 2. Why? Radius, equal radius. 2, 2, 2. Root 3, this is also root 3. So R has a radius equal to this 2 root 3 is a diameter, radius is root 3. Lovely. So with that we can find this area. What is that area? It is 1 by 2 into pi into root 3 square, just 3 pi by 2. That part is done, comfortable. Now let's look at the purple shaded area. This is the part of P, which also happens to be in R. This is a segment of P. Right? What is this arc? What is the central angle? The angle here is 120. So this purple area, this will be area of sector minus area of triangle. This is area of a segment. What is area of the sector? Angle at the center divided by 360 into pi r square. What is the radius here? Radius will be 2. What is the angle at the center? 120. And so let's write area of the sector, just 120 by 360 into pi into 2 square. What is area of triangle? The triangle we have in mind here. I'm going to again see if I can find a different color. The triangle we have in mind here is this triangle here. This segment, this sector minus this triangle. What is the formula I use? I can use AB is root 3, half into root 3 into 1. Half into base into height minus half, minus half into 2 root 3 into 1. Sorry, AB is 2 root 3 into 1. This is root 3. So I need to add this to this to get to our answer. 120 by 360 is 1 by 3. So this is 3 pi by 2 plus 4 pi by 3 minus root 3. So 3 pi by 2 plus 4 pi by 3 minus root 3. This is a minus root 3. This is out. This is out. This is out. 17 pi by 6 minus root 3 or 13 pi by 3. Denominator is 6. This is 9 by 6. This is 8 by 6. 17 pi by 6 minus root 3. That's the answer you're looking for. So beautiful, beautiful question. We're going to think about, draw the diagram nice and slow and then say, hey, this is a semicircle plus a segment. Segment is sector minus triangle. Semicircle we know, but the semicircle has a different radius. Segment, sector minus triangle, that is for a different circle. So do it methodically, carefully. Wonderful question, really challenging. ABC is a triangle with integer valued sides. AB equal to 1, BC greater than 1 and CA greater than 1. If D is the midpoint of AB, then which of the following options is the closest to the maximum possible value of angle ACD? First of all, integer sides. One side is 1. So think about it, integers, 1, x, y. If you say y is the longest side, we know 1 plus x is greater than y, or 1 greater than y minus x. Y minus x should be less than 1. Y and x are integers. Difference between two integers should be less than 1. How is that even possible? Difference between two integers, how can it be less than 1? It can be only one instance, y is equal to x. Or if a triangle has integer sides and one of the sides is 1, other two are equal. 166 is a possible triangle, 155 is a possible triangle, 144, 133, 122. But 156 doesn't work, 167 doesn't work, 1810 doesn't work. If one of the sides is integer, if one of the sides is 1, other two are integers, it has to be an isosceles triangle. So straight away we know that BC is equal to CA And so we are looking at triangles. The AB is 1, could be 1, 3, 3, 1, 2, 2, 1, 5, 5, something like this. And so AB is the base, C is here, D is here. We want to find the maximum possible value of angle ACD, maximum possible value of this angle. And so straight away we can sense that this base is set. You're taking it higher and higher, the angle will become smaller and smaller, or the maximum value will be when this is 1, 2, 2. Lovely. So let's do this. 1, 2, 2. Draw this triangle. C, A, B, 2, 2, D, 0.5, 0.5. We want to find maximum value of this angle. We call this angle as alpha. Then sine of alpha is 0.5 by 2, which is 1 by 4. Sine of alpha is 1 by 4. And so sine 30 is half. This is half of that. So our angle is definitely less than 30. Closest to the maximum possible value, closest to. So it is less than 30. So this is not this, not this, not this, not this. Sine 15 must be close to 1 by 4. I don't think it'll be 1 by 4 exactly, but it must be close to 1 by 4. That's the answer we're looking for. So we have to figure out some part, to make some geometry inferences. We need to find out where the ballpark is, and then after this we shouldn't say, look, this is sine inverse of cos of this, is find root 2, and etc, etc, etc. We can, even if we find the answer, we can't go anywhere with that. So we'll have to simplify it, switch off and say, hey, where are we, what is the ballpark for this, and then take a chance. A rectangular swimming pool is 50 meters long and 25 meters wide. So its depth is the same along its width. So I'm going to draw this pool. I find these things difficult to draw in 3 dimension. Let's draw this. Right. 50 meters long, 25 meters wide. Its depth is always the same along its width, but linearly increases along its length from 1 meter at one end to 4 meters at the other end. So here it is 1 meter. It keeps on increasing. Here it is 4 meters. How much water is needed to completely fill the pool? There are nice cuboid, it will be fine, simple. No, this is not. Right? The easiest way of doing it is this cuboid has length of 50, width of 25, and height average of 4 and 1. 4 plus 1 by 2. You're good to go. 50 into 25 into 4 into 1 by 2. 50 into 25 into 5 by 2. That is 25 into 25 into 5 meter cube. 625 into 5, 3125 meter cube. And so, how many cubic meters are required? 3125. Done. The more complicated way is to establish that it is 4 plus 1 by 2. How do we do that? We know that for a 3-dimensional thing, which is just vertically risen above, base area into height is a volume. Imagine the base to be this trapezium, the height to be this, the entire swimming pool tilted. Area of this trapezium, height is 50, sides are 4, parallel sides are 4 and 1. So area of trapezium is half into sum of the parallel sides into distance between the parallel sides. That base into a height of 25 is volume. That's the other way of imagining it, instead of just taking a 4 plus 1 by 2. 4 plus 1 by 2 works. 4 plus 1 by 2 is 2.5. So if you imagine the height of 2.5, whatever volume is lost here would have been gained here. That's the way of thinking about it. This is a simpler, quick and dirty way. This is slightly more elaborate, same approach. Answer is 3125. A rectangular field is 40 meters long and 30 meters wide. Draw diagonals on this field, 50 meters long, that much we know. So 30 and 40, draw diagonals and then draw circles of radius 1.25 meters with centers only on the diagonals. So some diagonal here. 1.25 meters is nice and small. We're drawing circles like this. Each circle must fall completely within the field. Only any two circles can touch each other but should not overlap. What is the maximum number of such circles that can be drawn in the field? Brilliant, brilliant. This is classic XAT. And so, first of all, this is 50. This is also 50. If radius is 1.25 meters, diameter is 2.5 meters. So let's worry about one diagonal. Diagonal of length 50. 2.5 meters. How many such circles can be placed? This is 2.5. So 50 by 2.5 is 20. On one diagonal, 20 can be placed. On another diagonal, another 20. So 40 seems like a legitimate candidate. However, the very crucial point, we are not just placing on the diagonal, we have to place on the diagonal, keeping in mind that they don't overlap. If there are 20 on this diagonal and 20 on this diagonal, the middle diagonals are going to eat into each other. There is an issue there. Right? Not just that. If you draw a diagonal right at the end with 1.25 meters gone like this, it will spill out. It will not sit inside a triangle. We need to worry about that. And so let's first worry about that it being inside and then think about it. So I'm going to think about the circle right at the end here. Draw a circle with radius 1.25. It has to be inside this rectangle. That means this distance, this will be radius from here, radius, the sides could be at best tangents. So you cannot draw a circle with this as center passing through this. Then it will cut like this. That doesn't work. It has to be at best tangent. Or you have to draw a circle like this, with this being 1.25. And so this triangle is neither ratio 3:4:5. This is the 4 side. So we should take this 3 side as the critical length. There will be some wasted space here. This also won't be tangent. It's not a square. This is 1.25. This is 1.25 into 4 by 3. This is 1.25 into 5 by 3. And so this is very crucial to remember that we cannot draw a circle that goes right up to this edge, right up to that vertex. We take one diagonal, not even coming to the second diagonal, we will lose out some length here. Right? So I'm going to imagine that length from the center. This distance is 1.25. So let's say this is O, this is A, this is P. OP is 1.25. OA is 1.25 into 5 by 3. AP is 1.25 into 2 by 3. There is going to be a 1.25 into 2 by 3 length, which is right at the end of the diagonal, which cannot have a circle. So that we are going to lose out in that 50 meter length of the diagonal. So keep that in mind. So 1.25 into 2 by 3 does not have a circle part. So in one diagonal, we cannot squeeze in 20 circles, which is why it's such a beautiful, delightful question. So if we take one diagonal, let's say we take diagonal AC, out of the 50 meters, we lose a 1.25 into 2 by 3 and another 1.25 into 2 by 3. And so a 2.5 into 2 by 3 is lost, a 5 by 3 is gone, and 1.25 into 2/3, 1.25 into 2/3, that is 2.5 into 2/3 is lost, 5 by 3 is lost, 1.67 is lost. Brilliant. So we cannot draw 50 by 2.5 on this. So out of the 50 meter length, we subtract 1.67, we get 48.33. Divide that by 2.5. Only that many circles can be drawn on this first diagonal. That takes us to 19. Brilliant. We cannot draw 20 diagonals on the first circle. 20 is too tight. That means it'll be right up to the edge. We'll have to go. We put 19 there. We put 19 here. We get 38. It looks like it could be 38. But again, there's a tricky part here. Here the tricky part is, look, we might have a 30 by 40 sitting here. We could have 19 circles here. But then, if you put 19 circles here, there's going to be a circle here. So, squeezing another 19 here is going to be tricky. Now, we already know that from this end, a 0.83 is lost. 1.25 into 2 by 3. 2.5 by 3 is lost. Here and 1.25 could be lost. So, if you look at this rectangle ABCD, call this meeting point as O. We know OB equals 25. We know that putting 19 is tricky. Right? So, because we're going to lose a circle right in the middle. Because there's an odd number of circles, 19. There's a chance that one circle is right in the middle. Maybe we'll shift it out, not make it right in the middle. That is possible. But even then, it's going to be a hindrance. And I'm going to take that scenario and see where we end up with. Assuming there's a circle right in the middle of radius 1.25. Let's see how much we can squeeze in. So, OB is 25, half of BD. From OB, right at this end, we lose 1.25 into 2 by 3. At this end, we lose 1.25. So, out of 25, we lose a 1.25 and we lose a 1.25 into 2 by 3. Fine. So, we will still get more than 22.5. Right? 1.25 plus 1.25 is 2.5. 25 minus 2.5 is 22.5. We still get more than 22.5. Or here we can squeeze 9 circles. Here we can squeeze 9 circles. 9 plus 9, 18. 18 plus 19, 37 is possible. 40 is not possible. 39 is not possible. 36 we don't have to worry about. Can we squeeze in 19 plus 19? That means on BD, do we have continuous length of 19 into 2.5? 47.5 can we get on BD to get 19. 18 is possible, that we have seen. Is 19 possible? 47.5 meters length, is it possible? We lose this 1.25 2 by 3, 1.525 2 by 3, definitely. That is gone. So we have only 48.33. There's got to be something spilling over from the center circle. Even if you squeeze a lot here, not right at the center. And that spillover is going to be better than this 0.83. So we cannot squeeze 19 onto BD if AC has 19. So BD can have a maximum of 18. 19 plus 18, 37. Extraordinary question. Extraordinary tough question. So extraordinarily tough. Compared to the freebies that do exist, this is a no-no. You have to worry about the 2 diagonals. You have to worry about squeezing in circles into the 1 diagonal. Remember that in the end, we cannot go right up to the tip. Evaluate that we can squeeze only 19 to a diagonal. But if you squeeze 19 to the first diagonal, we might not have room for 19 in the second one. Then worry about, can we squeeze 18? Prove that we can squeeze 18 in the second one for sure. Then fret about maybe we can squeeze the 19th one also. And then remove that possibility. So this is a joyful, wonderful question to have fun with in and of itself. And to be stayed away like the bubonic plague during the XAT exam. During the exam, I don't want to establish how much I can think about small circles inside a rectangle. I want to stay away. But afterwards, a lovely question. In the figure given below, the circle has a chord AB of length 12 centimeters. Lovely. Which makes an angle of 60 degrees at the center of the circle O. Wonderful. At center O, this is 60. So OAB is an equilateral triangle. So this is 12, this is 12, this is 12. The radius of the circle is 12. OQ is a perpendicular bisector of AB, intersecting chord AB at P, arc AB at M, and CD at Q. Wonderful line like this. Arc AB at M, chord AB at P and CD at Q. This is 6. This is 6. Further, OM is equal to MQ. OM is equal to OM is 12. OM is radius, which is 12, or MQ should also be 12. Brilliant. The area of the region enclosed by the line segments AQ and QB, AQ and QB, and the arc BMA, this. So this area is closest to. Brilliant, brilliant, brilliant question. Just drawing the diagram has taken us a while. MQ is 12, that we know. So how do we find this area? Shaded region is area of triangle ABQ minus area of segment AMB. Wonderful. Area of triangle ABQ, we can do a half into base into height, right? But we still need to find the height. Base could be AB, height we need to find. How do we do that? OAB is an equilateral triangle. This is a perpendicular bisector. This is an altitude. Equilateral triangle of side A, the altitude is root 3 by 2 times A. We have an equilateral triangle of side 12, or OP is root 3 by 2 into 12, which is 6 root 3. So PM is 12 minus 6 root 3. Therefore, we can find area of triangle ABQ. This can be found. And so PQ is 12 plus 12 minus 6 root 3, which is 24 minus 6 root 3. So we know the height PQ, we know the base AB, area of triangle ABQ can be found. Now that's not enough. We still need to worry about segment AMB. Let's worry about that. I'm going to redraw this diagram here just to recap everything. Wonderful. O, M, P, Q. OP is 6 root 3. PM is 12 minus 6 root 3. MQ is 12. PQ equals 24 minus 6 root 3. All good. So with this set of information, we can find area of triangle ABQ. That part is covered. Now we are looking to find this. This is nothing but sector minus triangle. Sector minus triangle. Sector, the central angle is 60 degrees, so it is 1/6 of area of circle. Sector is 1 by 6 into pi into 12 square. Minus triangle. Triangle is root 3 by 4 a square because an equilateral triangle. Root 3 by 4 into 12 square. Area of triangle ABQ equals half into AB into PQ, which is half into 12 into 24 minus 6 root 3. Or 6 times 24 minus 6 root 3, 6 and 24, 144 minus 36 root 3. Brilliant. So let's find this out. 1/6 of pi into 12 square. 12 square is 144. 144 by 6 is 24. So it's 24 times pi minus root 3 by 4 into 12 square. 144 by 4 is 36. 36 root 3. We need to subtract this number from this number. This minus 24 pi minus 36 root 3. This disappears completely. We're left with 144 minus 24 pi, or extracted 24 out. 6 minus pi. Pi is 3.14, so this is roughly 24 into 6 minus 3.14. 24 into 2.86. 24 into 3 is 72. 24 into 0.14 is 3.5 something. So 24 into 2.86 is 72 minus 3.5 4, roughly 69. So we're looking at 68.4, 68.5, roughly 69 square centimeters. Beautiful question. We're going to be very methodical about this. Mohanlal, a prosperous farmer, has a square land of site 2 kilometers. For the current season, he decides to have some fun. He marks 2 distinct points on one of the diagonals of the land. Using these points as centers, he constructs 2 circles. Each of these circles falls completely within the land and touches at least 2 sides of the land. To his surprise, the radii of both the circles are exactly equal to 2 by 3 kilometers. Mohanlal plants potatoes on the overlapping portion of these circles. Calculate the area on which Mohanlal planted potatoes. Lovely, lovely, lovely question. So let's draw the square. Square of side 2 kilometers. He marks 2 distinct points on one diagonal. So diagonal, say square is ABCD. The diagonal BD is 2 root 2 kilometers. He constructs 2 circles. Each of these circles falls completely within the land and touches the other 2 sides. Are exactly 2/3 of a kilometer. 2/3 of a kilometer and touches this. So some center somewhere here. This is 2/3. This is 2/3. So we are drawing a circle like this. Likewise, from somewhere here, this is 2/3, this is 2/3. We're drawing a circle like this. This is 2 by 3, this is 2 by 3. Let's say this circle as a center of P, this circle as a center of Q. Lovely. We want to find the, what does he do? He plants potatoes on the overlapping area. That is this area, this region. He plants potatoes. Let's find some simple lengths. We know BD is 2 root 2. A nice square. So DP is 2 by 3 root 2. The square. A 45-degree angle. 2 by 3, 2 by 3, 2 by 3, 2 by 3. QB is also 2 by 3 root 2. Lovely. Radius is 2/3. Is 2/3 root 2. 2 by 3, 2 by 3. And so 2 root 2, I'm going to write it as 6 root 2 by 3. There's a 2 root 2 by 3. This is 2 root 2 by 3. This is 2 root 2 by 3. Overall distance is 6 root 2 by 3. Or PQ is also 2 root 2 by 3. Lovely. So let's join this common chord and call that, say, MN. So if we find the area of this segment and then we double it, we are through. How do you do that? Join PM, join MN. Lovely. So this is 2 root 2 by 3, that is PQ. And so PM is 2/3, PN is 2/3. We need to still find area of that segment M, and either this part or this part, it doesn't matter. Let's say we call this KNLM, either MLN or MKN, that segment, both of them. And so MQ is 2 by 3, QN is 2 by 3. Fine. PQ is 2 root 2 by 3. Now just think 1 second. I'm going to 2 by 3, 2 by 3, 2 root 2 by 3. I'm thinking about triangle PMQ. The sides are 2 by 3, 2 by 3, 2 root 2 by 3. PMQ. PM is 2 by 3, MQ is 2 by 3, PQ is 2Q by 3 are there in the ratio 1:1 root 2, or there's a right angle sitting here. PMQ is a right angle. This is a right angle. So this is a nice rhombus with one angle of 90, or we're dealing with a beautiful square. This makes life very easy. Finding area of this segment suddenly became very easy because we're thinking about one quarter circle minus area of a triangle. So we're going to isolate this segment. So that segment is 1/4 of pi into 2 by 3 square minus half into base into height, half into 2 by 3 into 2 by 3. The sides are 2 by 3 and 2 by 3. That's the radius. So pi by 4 into 2 by 3 square minus half into 2 by 3 into 2 by 3. That is the area of that segment. But our good man is not just cultivating this, he is cultivating twice of this. Wonderful. Or we are looking to calculate 2 times of pi by 4 into 2 by 3 square minus 1 by 2 into 2 by 3 into 2 by 3. Take away the 2 by 3 square outside. 2 into 4 by 9 whole into pi by 4 minus 1 by 2. This 8 by 9 into pi minus 2 by 4. 2 by 9 into pi minus 2. 2 by 9 into pi minus 2. Thankfully, that choice exists. Otherwise, we would have spent so much time on a wild goose chase. And once again, excellent question. Methodically, we can solve it. In a lot of these questions, back yourself to find something special. Given the distance between the two centers and the radii, you'll get either an equilateral triangle or an isosceles right angle triangle. So anything else, this question becomes impossibly tough. It turns out that that shape PMQN, that beautiful, delightful shape in between, is a square. If we are not a square, we're running on a wild goose chase. Because it's a square, life becomes simpler. So back yourself to find something featuresome like that, and then solve methodically. Intersection of lines. Let P be the point of intersection of the lines 3x plus 4y equal to 2a. Like this 2a. 7x plus 2y equal to 2018. Large number. And Q be the point of intersection of the line 3x plus 4y is 2018 and 5x plus 3y equal to 1. The line through P and Q has a slope of 2. The value of A is. And so, first thing to notice that we can find Q. We can locate Q somewhere. And then we know that through Q and P, the line has a slope of 2. Using that, we can find A. So that's the idea. Q we can find. That's the point of intersection of these two lines. So we can locate Q, and then we can get P in terms of A, and then use the idea that PQ has a slope of 2 or something along those lines. First up, I'm going to find point Q. Right? So it's a very time-consuming question, and it's a tricky question. I tried to get a lot of juicier approaches for this, but the old-fashioned one is probably the best. Right? 5x plus 3y equals 1. We can multiply this by 5 and this by 3 and locate x comma y. And the 15x plus 20y is 5 times 2018, which is 10,090. 15x plus 9y equals 3. Brilliant. 15x plus 20y is 10,090. 15x plus 9y equal to 3. Subtract 1 from the other. We get 11y equals 10087. 1 plus 0 plus 7 is 8. 0 plus 8 is 8. This is a multiple of 11, thankfully. So we can find y. Y is 10087 divided by 11. It goes 9 times 99, 1 times 11, and 7 times. Y is 917. 5x plus 3y is 1. 5x plus 3 into 917. 3 sevens are 21. 1, 2, 3 plus 2, 5. 2751 equals 1. Or 5x equals minus 2750. X equals, divide this by 5, minus 550. Or Q is the point minus 550 comma 970. Quite brilliant. And now we can find P similarly in terms of Q and then find this. But we know that PQ has a slope of 2. We can take a slightly different approach. Form equation of PQ. How do we know that? We know a slope, we know a point. You can say y minus y1 is m times x minus x1, or y minus 917 is 2 times x plus 550. And so this is the equation of PQ. So P should lie on it. The point of intersection of these 2 points should lie on this line, or the 3 lines are all concurrent. All 3 lines pass through P. These 2 lines meet at P. This line passes through P. Or the 3 lines that we have, 3x plus 4y equal to 2a, 7x plus 2y equal to 2018, and this line, they all pass through P. So if we solve this and this, we'll get P. Substitute the points of x and y here, we'll get A. Brilliant. So let's find this equation. Y minus 917 is 2x plus 1100. Or 2x minus y, taking this y this side, this minus 917 minus 1100, or 17 and plus 110, 01, minus 2017. Okay. Brilliant. Now we need to solve for 7x plus 2y equals 2018 and 2x minus y equals minus 2017, and then get values of x and y, which will be the coordinates of P. Substitute that x and y, which is maybe x1, y1, the solution of this, into this expression, and then find A. Whew, time consuming. Right? Now comes the juicier, softer, wonderful bit. We have to go in to find x and y, get the values of x and y, and plug this into this. Is there a way of manipulating these 2 expressions to get 3x plus 4y? To get 3x, we can multiply this by 2 and subtract. We multiply this by 2, we'll have minus 2y. We subtract, you'll get 4y. Or brilliant. We multiply this equation by 2, you get 4x minus 2y is minus 4034. Now forget this. Subtract this from this. We'll get 3x plus 4y equals 2018 minus 4034. This is 2a. 2a equals 2526052, or A is 3026. Wonderful question, delightful question, but very tough. More than tough. There's nothing magically difficult conceptually here, but very, very time consuming. The coordinate geometry questions are going to be time consuming. This one particularly so. Let C be a circle of radius root 20 centimeters. Radius is root 20. Let L1 and L2 be the lines given by 2x minus y equal to 1. 2x minus y equal to 1. And x plus 2y equal to 18. And so let's think about this. 2x minus y equal to 1. If we put y equal to 0, we get x is half comma 0. If we put x equal to 0, we get y is minus 1, 0 comma minus 1. So it's a line like this. This is L1. L2 is x plus 2y. So this is half comma 0 and 0 comma minus 1. X plus 2y equal to 18. When y is 0, x is 18. So the point 18 comma 0. When y is 0, x is 18. When x is 0, y is 9. 0 comma 9. It's a line like this. This is L2. Suppose that L1 passes through the center C and that L2 is tangent at the point of intersection of L1 and L2. So L1 passes through the center and L2 is tangent to C at the point of intersection of L1 and L2. A comma B is the center of C, and so A comma B can be here, and this point of intersection is there. L2 is tangent to C at the point of intersection, and so these two lines are perpendicular. So this is a radius, this is a tangent, and so we find A comma B, and then the distance from A comma B to point of intersection should be equal to the radius. Then it will be a tangent. Radius is square root of 20 centimeters. This is root 20. A point on this line passing through this point, point on this line with the center with radius 20. If you draw a circle, it'll be root 20. It should be tangent at this point. That's what we are looking at. Fine. First up, let's find where these two intersect. 2x minus y equal to 1. X plus 2y equal to 18. Let's multiply this by 2. 4x minus 2y is 2. If we add these two, 5x is 20, x is 4. And if we get x is 4, we can find x. We can find y. 2 into x, 2 into 4 minus y is 1. 8 minus y is 1. Y is 7. This point is 4, 7. Fine. So, and then we want the center. Suppose that L1 passes through the center. L1 is the line 2x minus y equal to 1. This is L1. The center is somewhere here, not here. L1 passes through the center and this is a distance of root 20 from 4, 7. Wonderful. L1 is 2x minus y equal to 1. Or if we put x is equal to t, 2t minus y equal to 1, or y equals 2t minus 1. The point is t comma 2t minus 1. The other point, the point of intersection is 4, 7, and this distance is root 20, or square root of t minus 4 the whole square plus 2t minus 1 minus 7 the whole square equals root 20. Brilliant. This is t minus 4 the whole square plus 2t minus 8 the whole square, or 4 times t minus 4 the whole square, which is square root of 20. Or this is t minus 4 the whole square root 5, and this is 2 root 5. Brilliant. So this is t minus 4 the whole square into root 5, which is equal to, t minus 4 times root 5 is 2 root 5. And so t minus 4 whole square, or modulus of t minus 4 times root 5 is root 5, or t minus 4 could be 2 or minus 2. T is 6 or 2, both work. T could be 6 or t could be 2. Brilliant. So t is 6 or 2. So t could be t comma 2t minus 1 are the point A and B. T could be 6, in which case 2t minus 1 would be 2 into 6 minus 1, 12 minus 1, 11. Or t could be 2, be 2 into 2 minus 1, which is 4 minus 1, 3. A plus B could be 5 or 17. 17 is a possible answer. Absolutely delightful, brilliant question. What we are doing here, trying to draw the two lines, find the point of intersection. Then we are saying on L1, we'll find the general coordinates. Take the general coordinates of that point, mark the distance between that and 4, 7 to be equal to root 20, and solve for the point of intersection. You'll get an A comma B here and an A comma B here. This does not work for possible values. This one does work for total being 17. It's a tough question, time consuming question. From the point of view of the exam, you're probably better off skipping it. In the trapezium ABCD, AB and CD are parallel. The value of sine angle BAC to sine angle BAD. Wonderful, wonderful, wonderful question. Fine. So we've got to use the idea that we are talking about two parallel lines. I'm going to call this angle as alpha, this angle as beta. This is alpha, this is alpha. alternate interior angles. If this is beta, this is 180 minus beta. We know that sine x is sine of 180 minus x. Right? So now think about this. We can try to link these two angles, or we can link this angle to this angle, or this angle to this angle, or this to this. Something involving beta, something involving alpha. If we can link, we are through. And we have a wonderful link there. I'm going to think about triangle ADC. This is alpha. This is 180 minus beta. Right? So think about this. A by sine A is equal to B by sine B equal to C by sine C. Or sine alpha by AD equals sine of 180 minus beta by AC. We are through. We are clearly through. Think about how we are through. So sine alpha by sine of 180 minus beta is AD by AC. Bringing this here. Sine of 180 minus beta is sine of beta. Angle BAC is alpha, BAD is beta. We've already made that assumption here. We're looking for an answer that is AD by AC. Found that. Use the idea that these two lines are parallel, and use the idea that of sine rule. So make sure that you know this is equal to this, and that this whole angle and this angle are supplementary, and sine x equals sine of 180 minus x. Beyond this, in any triangle, A by sine A equals B by sine B equals C by sine C. Sine rule and some parallel line, alternate interior angles, co-interior angles ideas, and we are through. Once again, tough question, not at all easy. The picture below, EFGH and ABCD are squares, and ABE, BCG, CDG, DAH are all equilateral triangles. What is the ratio of the square EFGH to that of square ABCD? Right, so let's say the side of this square is A, side of this square is B. We find A is to B, we are through. We can then find area as A square is to B square. That's very simple. In all of these questions, make sure you can link one dimension of one shape to some dimension of the other shape. We are through. So this is A, this is A. What is the link point? I love HF. I know H into F is 2 times, root 2 times B. That we know. HF is also altitude, and square. So HF equals A plus 2 times root 3 by 2A. Or A into 1 plus root 3 is root 2B. We want to find the ratio of areas EFGH to that of ABCD, or we want to find A square by B square. We have A by B. What is A by B? A by B is root 2 by 1 plus root 3. What is A square by B square? That is going to be root 2 by 1 plus root 3 whole square, which is 2 by 1 plus 3 plus 2 root 3, or 2 by 4 plus 2 root 3, or 1 by 2 plus root 3. Ratio is going to be 1:2 2 plus root 3. Ratio of the area of square EFGH to that of ABCD 1:2 2 plus root 3. It should be 1:2 root 3 plus 2, and 1:2 part is missing. We all know what we are talking about. 1:2 plus root 3. What are the maximum number of points that can be placed on a circular disc of radius 1 meter on the bounding circle of the disc, such that no 2 points are at a distance of less than 1 meter from each other? Now, every point you place inside, you are limiting yourself, likely to be placing it outside. Right? So think about this. The wonderful thing that we know, the radius is 1 meter. Right? We mark a chord of 1 meter length. Then you will get an equilateral triangle. If you put 3 points like this, then no 2 points are less than 1 meter from each other. And we can put one more like this, one more like this, one more like this, one more like this. Here we have placed a bunch of points which are all at exactly 1 meters from each other, from the nearest points. From here, if you put a point in the center, then you cannot put any point inside the circle. We want to put as many points on the boundary. We can put maximum of 1, 2, 3, 4, 5, 6 on the boundary. If we put all of these 6, then we can put 1 in the center. That's it, nothing more. So we can get 7 points. Another way of thinking about it, take a point, mark a point 1 meter from it. You draw out a circle. There can be no other point in this region. Inside that, so then it will be. So from here, mark out another arc of radius 1 meter. Locate a point here. Locate a point here. This is the best case scenario with 1 meter distance. And from here, with these 2 points, mark another with 1 meter. With these 2, mark another with 1 meter. With these 2, mark another with 1 meter. Luckily enough, this is also 1 meter. Or we get a bunch of points, which will all be inside 7 points. A regular hexagon and its center inscribed inside the circle. The vertices and center, that's what you're looking for. The figure below shows 2 right angle triangles, triangle OAB and OQP, with right angles at vertices A and P respectively, having common vertex at O. The lengths of the sides are indicated in the figure. AB and OP are parallel. AB and OP are parallel, or this angle is 90. This is 90. This should be 90. Find angle QOB. We need to find this angle. If you find this and this, we can find this. 90 minus angle POQ minus angle BOA. There's some 60 degree, some tan inverse mentioned. Good chance that we are using some trigonometry. BOA, we're going to call it alpha. This we're going to call it beta. We're looking at 90 minus alpha minus beta. Okay. Tan alpha is 1 by 3. Tan beta is 1 by 2. That's it. We're done. We can answer this question merrily using some trigonometry. We want to find 90 minus of alpha plus beta. If we find alpha plus beta, we are through. We know tan alpha and tan beta. We're going to use the idea. Tan of alpha plus beta is tan alpha plus tan beta by 1 minus tan alpha tan beta, or tan of alpha plus beta is 1 by 2 plus 1 by 3, but 1 minus 1 by 2 into 1 by 3. So it's 5 by 6 by 5 by 6. 1 by 6, 1 minus 1 by 6 is 5 by 6. 3 by 6 plus 2 by 6 is 5 by 6, which is 1. Alpha plus beta tan is 1, or alpha plus beta is 45. This angle plus this angle is 45. The remaining should also be 45. Alpha plus beta is 45. Remaining should be 45. That's the answer we are looking for. Let ABC be an isosceles triangle. Suppose AB and AC are equal. Let the length of AB be x centimeters. And so AB and AC are equal. A, B, C, X, X. Let B denote the angle ABC. Sin B is 3 by 5. Right? Sin B is 3 by 5. If the area of triangle ABC is m square centimeters, m, which of the following is true about m? Fine. So think about it. M is the area. If you call this angle as A, area is half x square sin A. Brilliant. This is B. This is also B. These two angles are equal. Sin B is 3 by 5. Right. So let's think about B plus B, sin 2B. B is an acute angle, that much we know. If sin B is 3 by 5, then cos B is 4 by 5. I'm going to account for 2B and 2B. This angle A is 180 minus 2B. So we're looking at half x square sin of 180 minus 2B, or half x square sin of 2b. If we find this, we are through. We need to find a range for that. So we know that sine b is 3 by 5, so we can find sine 2b. Cos b is 4 by 5. Sine b is 3 by 5, cos b is 4 by 5. Technically speaking, cos b can be minus 4 by 5 also. We'll worry about the minus part later. Sine 2b is 2 sine b cos b. 2 into 3 by 5 into 4 by 5. 2 into 3, 6 into 4, 24. 24 by 25. So area half x square sine 2b, which is half into x square into 24 by 25. This is m. M equals 24 or 12x square by 25. And so m sits between x square by 4 and x square by 2. Yeah, that is right. This is less than x square by 2. This is wrong. Greater than or equal to x square. That is wrong. Between x square by 2 and 3x square by 4. That is wrong. Less than x square by 4. That is wrong. This is the answer you are looking for. We can find the exact value of m. M is 12x square by 25. Slightly less than half x square. That's what we are looking for. And so again, sine rule. We know that area of a triangle is half x square sine a. We know a is 180 minus 2b. We know that sine of 180 minus 2b is sine of 2b. We know sine b. We can find sine 2b. Plug in sine 2b, you're through. Don't worry about cos b being minus 4 by 5 because this cannot be an obtuse angle because the equal angle in an isosceles triangle cannot be obtuse. The diagonals of a rhombus of side 15 centimeters are the ratio 3:4. Diagonals of a rhombus are perpendicular bisectors of each other. You should know that, otherwise we are on a dead end. So we have a rhombus like this. Diagonals of a rhombus are perpendicular bisectors of each other. They are the ratio 3:4. This is half of this diagonal, half of that diagonal. This should also be in the ratio 3:4. This is the ratio 3:4. This is 5. This 5 thing corresponds to 15. So the 3 should be 9. This should be 12. Or the entire diagonal is 9 plus 9, 18, 12. The diagonals of the rhombus measure 18 and 24. Area is half into product of diagonals or 9 into 24, which is 216 square centimeters. Let's look for that choice. It's not available. Dangerous. I hate these none of the above one. This one I'm confident, so I'm plugging in 216. Let's do this one. A girl travels along a straight line from point A to B at a constant speed of v1 meters per second for t seconds. So A to B. B to C along a straight line at a constant speed of v2 for another t seconds. BC makes an angle of 105 with AB. This is 105 degrees. This is v1 for t seconds. This is v2 for t seconds. How much time would she take to travel back from C to A at a constant speed of v2 if she travels in a straight line from B to A? See, the straight line does help. So this is 30 degrees. 105 plus 30 is 135. So this one should be 45 degrees. She's traveling at v2. We want the time for which she travels. Wonderful. So we've been given the 3 angles of a triangle. Given 3 angles, the sides have to be in a specific ratio. Once we crack that ratio, we should be through. She's traveling at a speed of v2. And so v2 t seconds, v2 for how much seconds? And so we know the famous rule, which is a by sine A equals b by sine B equals c by sine C. So if we take BC, the distance BC by sine 45, which is sine A, equals AC by sine 105. And so BC is V2 into T, and AC by sine 105. We need to find AC or BC into sine 105 by sine 45 equals AC. I'm going to use sine rule here because I know that. If you don't know, you can still figure sine 105 out. Sine 105 is, so this is BC into Sine 60 cos 45 plus cos 60 sine 45 by sine 45. Luckily enough, sine 45 is equal to cos 45. So this is out. This AC. Sine 60 is root 3 by 2. Cos 60 is 1 by 2. So BC into root 3 by 2 plus 1 by 2 is AC. So BC is V2 into T. So the time taken would be T into 1 by 2 into root 3 plus 1, or T into 0.5 into root 3 plus 1. 1 by 2 is 0.5, root 3 plus 1 is what we got remaining. That's a simple application of sine rule once you get this sense that this is a triangle where all three angles are known. The moment you have a triangle where all three angles are known, and you know the angles to be your friendly 30, 45, 60s, 90s, then plug in sine rule and we are through. It's an absolutely brilliant question. It's a question that you should definitely try. Probably very difficult to do it in an exam context, but you should definitely try this question. Fine. So, two circles with radius 2r and root 2r, radii 2r and root 2r, intersect with each other at points A and B. So 2r and root 2r, 2r, root 2r. The centers of both the circles are on the same side of AB. So clearly, this diagram is wrong. We're looking for a diagram like this. This being AB. This itself is difficult to get. So keep an eye on this. O is the center of the bigger circle. So O is the center of the bigger circle here. Angle AOB is 60 degrees. Bigger circle is 2r, smaller circle root 2r. Find the area of common region between the two circles. So we're looking to find this area. Wonderful question, really nice, tough question. So I'm going to draw the diagram out first and then reimagine this question. And so to start with, I'm going to call the centers with two circles as O1 and O2 because we're going to have two centers. And so large circle and small circle intersecting like this. I'm going to think about this common between these two. I'm going to imagine this as this area plus this area. Right. First step, let's do some simple geometry. So the radii of the large circle is 2r, this angle is 60 degrees. So we're looking at an equilateral triangle. So this will be 2r, 2r and 2r. Right. So now if you imagine the smaller circle, this is root 2r, this is root 2r. The ratio of the sides is root 2 is to root 2 is to 2, or 1 is to 1 is to root 2. This is an isosceles right angle triangle. This angle here is 90 degrees. It really helps. And so the area common between these two circles is area of the smaller circle minus this sliver here, this crescent shaped piece. Or another way of thinking about it is if you think about the smaller circle and we think about this space, this is a segment, a major segment. Come to the larger circle and think about this region, this is a minor segment. So for the smaller circle, we can extract the major segment. For the larger circle, we can think about the minor segment and then add these two up. We should get area common between these two. And so let's go right ahead and do that. And so let's look at the large circle first. So large circle, this is 2r, 2r, 2r. We want this area of the sector minus area of triangle. Area of sector is 1/6 of pi into 2r whole square minus root 3 by 4 into 2r whole square. And so this is pi by 6 into 4r square, or pi by 3 into 2r square minus root 3 by 4 into 4r square minus root 3r square. This is area of the small segment here, minor segment of the large circle. And so pi by 3 into 2r square, because this is 1/6 of the circle, angle in between is 60 degrees, 60 by 360, 1/6 of pi r square, radius is 2r, we've got this down. Next up, we're going to think about the smaller circle. This angle is 90, So remaining is 270 or 3 quadrants. 3 by 4 into pi into root 2r whole square plus area of this. This is root 2r, area of the triangle is half into root 2r into root 2r. These two get knocked off. We have an r square here, which becomes 2 by 2r squares become 3 by 2 pi r square plus r square. Now we're going to put these two together. So we're going to add up 2 by 3 pi r square minus root 3 r square plus 3 by 2 pi r square plus r square. Let's put the pi's together. 3 by 2 is 9 by 6, 2 by 3 is 4 by 6, 9 by 6 plus 4 by 6 pi r square minus root 3 r square plus r square, or the area would be 13 by 6 pi r square minus root 3 r square plus r square. Let's see if that matches with one of the choices that we have. 13 by 6 plus 1 minus root 3 r square is the answer. Absolutely wonderful question. One question like this can get all your ideas in mensuration crystal clear. Anything to do with circles, sectors, segments, you're through. So even if it takes you 15 minutes, 18 minutes, 20 minutes, hang in there, get it right. You see the whole structure and get it right, then you're through and home.